Okay, hello everyone. Today we are going to take a look at the third lecture of our Unit 15, and we're going to look at the Bronsted-Lowry definition of acids and bases. Here are our learning targets, and our big kind of target that we're going to do is classify based on this new definition. We're going to add on to the Arrhenius definition, and we're going to describe how we can qualitatively and quantitatively illustrate whether a solution is acidic, basic, or neutral. So let's get started. Okay, yesterday we highlighted that ammonia brings up this problem for us when we're just looking at the Arrhenius definition of an acid or a base, because according to this Arrhenius definition, we are trying to produce hydroxide. We're looking for something that produces hydroxide, as well as turns litmus blue. And ammonia turned litmus blue, but it does not contain a hydroxide ion. Ammonia also can be used to neutralize hydrochloric acid solutions. So if something turns litmus blue and can neutralize hydrochloric acid solutions, it is a base. So we have to kind of take on another definition for what is a base. And so what we're going to explore is the Bronsted-Lowry definition of acids and bases. There we go. So ammonia does what an Arrhenius base does, practically speaking. And what it does is it dissociates a hydroxide ion in the water solution. So we are still ending up with a hydroxide, but it is causing water to give up the hydroxide. And let's take a look at this reaction to kind of highlight this. So when we are looking at this, what we see happen with ammonia is it goes from NH3 to this ammonium ion. So it gained a proton. So it gained a proton, an H+, and we know that because we're looking at H3 here, and now we have 4 hydrogens. Water, on the other hand, lost a proton. So we've got 2 hydrogens here, and now we have OH, which is one species. So it lost a proton. It lost a proton, or it donated it. Okay, and this is our definition of a Bronsted-Lowry acid, okay? Something that donates a proton. So this is a Bronsted-Lowry acid, something that donates a proton. And ammonia fits our definition of a Bronsted-Lowry base, okay? A Bronsted-Lowry base is something that, okay, so this is a Bronsted-Lowry base, and this is something that accepts a proton. So remember, we can use proton, and we're talking about H+ when we're talking about protons. Okay, let's look a little bit more closely at how we can name these things. So Bronsted-Lowry definition, any reactant that donates a proton to another reactant. So the water, in this case, was our proton donor. Okay, so we said that this was the Bronsted-Lowry acid. So this was our acid because we donated an H+. Okay, and the ammonium, we said, the ammonia becoming ammonium was our base. Okay, our base is anything that accepts a proton from another reactant. So ammonia accepted, we know that because on the reactant side it has 3 protons, it's got 3 hydrogens, and here it's got 4 hydrogens, so it accepted. So this is our base, okay? So ammonia is our base. These are on the reactant side, okay? So we are labeling acids and bases on the reactant. And we've got another name that we're going to name the products, okay? So we're going to see a different name for the products. So our key, okay, we look for something that donates a proton, so something that loses a proton, that would be our acid, okay? So acids donate, and bases accept. So we can use kind of the words to think about this, okay? So the base, ammonia, accepted a proton here. So what do we name the product side? Okay, we call the product side, we call these our conjugate acid and our conjugate base. Okay, so on the product side, these are what we're going to label with the word conjugate. Okay, and our goal is to, here is our goal. Okay, our goal is to locate the base. And if we locate the base, then we have the rest of anything that we need to name. Okay, so let's go back and let's label our acid again. So water was our acid according to the Bronsted Lowry theory, and ammonia was our base. Okay, because it accepted and the water donated the proton. So the Bronsted Lowry definition of a conjugate acid, this is the resulting product. Okay, so anytime we're on the product side, we're using the word conjugate, formed from the Bronsted Lowry base accepting a proton. So once you find your base, whatever accepted that proton is your conjugate acid. So I'm using Ca as the conjugate acid. And we can think, if we want to think about this, we can think about the reaction in reverse. Okay, so just think reaction in reverse. Because if the reaction moves from right to left, here, NH4 goes from having 4 hydrogens to having 3. So in that case, it would have donated, making it a Bronsted-Lowry acid. So we call it the conjugate acid in that case. Once we've located the base, we've located the conjugate acid. If you have the base, you have the acid on the reactant side as well. So here, the reactant product formed from the acid donating is what we call the conjugate base. So here's our acid that donated, and it becomes the conjugate base. So once we find the base, we know what our conjugate acid is, whatever gained the proton. And once we find the acid, we know the conjugate base, it is whatever gave the proton up. Okay, so acid gave it up. Whatever it ended up becoming is the conjugate base. The base accepted it. Whatever it becomes is the conjugate acid. Okay, so let's look at this a little bit closer here. In this case, water, okay, so the same reaction, water donated the proton. So it was behaving as an acid because it donated this. And it forms the conjugate base, OH minus. So the conjugates always go on the product side. Ammonia accepted the proton, and so this is behaving as a base because bases accept, okay, bases accept the H+. So ammonia accepted the H+, so it was our base, and it becomes the conjugate acid. So here was our base, and it became the conjugate acid. Water was our acid, and it became the conjugate base. Okay, so find what it becomes, and then we can label them. Okay, so pause this video. I'm going to go ahead and complete these. So we're going to label each as the acid, base, conjugate base. Remember, what we are looking for is what donates, okay, what donates. So according to Bronsted-Lowry, acids donate, acid donates, and bases accept. So we'll look at the reactants, we'll look at the products, we'll see what lost a proton, we'll see what gained a proton. So pause this, give this example a try, and come back and check your solution. Okay, so here is our solution. So in this first example, we can look at NH3, and it donated a proton. And I know that because it has 1 less hydrogen. So this is our acid. Remember, everything on our reactant side is either going to be acid or base. And everything on our product side is either going to be the conjugate acid or the conjugate base. So if we want kind of like a process here, label the acid, find what it becomes, and that is what it becomes is the conjugate base. Okay, so NH3 becomes NH2, It's our acid because it gave up a proton. There's our conjugate base. Actually, what I want us to do is, instead of looking at these specific Kb values, I actually want us to just not take notes on this slide. And then we're going to do the same thing with this hydrofluoric acid. Okay, so we're just going to skip these two examples. What we're just looking at are these K equilibrium constant for the acids and the base, but we're not going to get into detail on these. So I want us to keep moving. Okay, ultimately, what we need to gather from those is that the larger the value of Ka, the stronger the acid. Similarly, the larger the value of Kb, the stronger the base, which we labeled on the slide 2 previous to those as well. Okay. So auto-dissociation or auto-ionization. When we are talking about water, water dissociates into hydronium and hydroxide to a small degree. So when we have liquid water, to a small degree, what we're going to get is a hydronium concentration and a hydroxide concentration. So this is our equilibrium constant for water for its auto-dissociation. This is what we can use to determine quantitatively how acidic or basic a solution is, okay? So what we're going to look at is these two. This is going to be kind of the most important thing that we're going to use quantitatively for calculations, are the fact that when we multiply these two concentrations together, right? Okay, so here's our aqueous. When we write this expression, aqueous, these both are liquids, so we're not going to include them in the equilibrium expression. It equals 1 times 10 to the negative 14th. Okay. And this is the thing that we just have to wrap our heads around. So at all times, water is both an acid, a base, and neither. So water can function as a proton acceptor, it can function as a proton donor, and it can function as neither. These two things are equal because water has a neutral pH. Okay, so water is neutral. So our concentration of hydroxide and our concentration of protons are neutral. We get more acidic when our concentration of protons is increasing, or we get more basic when our concentration of hydroxide is increasing. Okay, so let's look at how we can use this. All right. If we have a greater concentration of hydronium, so we also could think, right, H plus concentration, then we're going to be acidic. So if we have a greater concentration of hydronium than hydroxide, we're acidic. So if we look at a graph of this, I've got way more hydronium, less hydroxide, that's an acidic solution. Or conversely, H3O plus is greater than 1 times 10 to the negative 7th, because this is a neutral point, right? If both of these are equal to each other, then it's neutral. So neutral, H3O plus equals OH minus. They both would be 1 times 10 to the negative 7th. If it's basic, we've got more hydroxide, okay? So more hydroxide if it's basic. So our OH minus concentration is higher in a basic solution. Or hydronium is less than 1.00 times 10 to the negative 7th. So we've got less than 1 times 10 to the negative 7th here. Okay, we can use this to complete quantitatively some calculations. Okay, so here are the steps for a calculation like this. We've got our equilibrium expression. So 1 times 10 to the negative 14th equals our concentration of hydronium times our concentration of hydroxide. So let's look at an example. We've got the given hydronium concentration, and we want to know what would be the OH minus concentration. So first step is to write Kw expression. So Kw equals 1.0 times 10 to the negative 14th, which is equal to H3O plus concentration times OH minus concentration. Okay, then we solve for OH minus. So if we divide each side by OH minus, we end up with this expression right here. So OH minus concentration is equal to 1 times 10 to the negative 14th over concentration of H3O plus. And this is given, okay, so now we substitute. So this equals 1.0 times 10 to the negative 14th divided by 1 times 10 to the negative 5th, given in the problem. And then we solve for what our OH minus concentration is. And what we end up with is this ends up being 1.0 times 10 to the negative 9th. Okay, so now we can identify if that solution would be acidic or basic. So this is our concentration of OH minus, okay, 1 times 10 to the negative 9th. So we can go back and look at our chart here. So we've got 1.0 times 10 to the negative 9th. This is our concentration of OH minus. We also were given the concentration of H3O plus in that problem, and it was determined to be 1.0 times 10. It was determined to be 1.01 times 10 to the negative 5th for our H3O plus. And now we can just classify this. And what's our H3O plus? Our H3O plus is greater than 1 times 10 to the negative 7th at 1 times 10 to the negative 5th. So we got to think about these scientific notation. Or, okay, H3O plus is greater than OH minus. So this would be an acidic solution. Okay, so this would be acidic. So acidic because concentration of H3O plus is greater than concentration of OH minus. Okay, so that was the second checkup for how to do this. So you guys try. Okay, we've got one more checkup. So pause this. I've got the steps down here that you can use to help you solve this problem. And so first we're going to calculate the OH minus concentration. So we're going to run through these steps and then determine if it's acidic, basic, or neutral based on the comparisons between H3O plus and OH minus. So pause this, give this a go, and I will put the solution up. Okay, so here's our step-by-step to solve for the concentration of OH minus. So we end up with 2.6 times 10 to the negative 11th. And if we go back to the beginning of the problem, we see the concentration of H3O plus, okay, so which is in right here, 3.9 times 10 to the negative 4th molar. And this is greater than 1.0 times 10 to the negative 7th. So if H3O plus is greater than this value, it's acidic. So this leads us to B. Okay, if you have any questions, please let me know. I hope you guys have a great day.